I'm Rajiv Shah. I'm a data scientist with Data Robot. I'm also an assistant adjunct professor at the University of Illinois at Chicago.
So we're going to discuss a paper and some work in deep learning and an application of it. But before we get into that, I'd love to know a little bit more about your background and perhaps, if at all, does it overlap with fields that study earthquakes and things like that?
My background doesn't overlap with any earthquake studies, but I do have quite a bit of a variety of a background where I started off as an engineering, didn't want to do engineering, went and studied philosophy, studied law, ended up getting a communications PhD, did research for a number of years as an academic, then later switched over into data science, kind of worked at places like State Farm and Caterpillar, and then my current employer is Data Robot.
In terms of like deep learning, are there any particular, I know it can be applied in so many places. Do you have a particular affinity for applying it to any types of problems or industries or things like that?
No, there's so many cool things you can do with deep learning. I've played around with deep learning, for example, applying it to motion data that comes out of the NBA, where players move around the court. Lots of other cool things you can do with images, with video as well. For example, the motion tracking of how you can watch how people's arms and legs move in those pose nets, I think are totally fascinating and cool.
So I'll ask a somewhat rhetorical question, but is all this deep learning stuff for real? Is this smoke and mirrors? Can this technology really do things for us?
The power of deep learning has really enabled us to now build so much better predictive models when it comes to areas like images and video. So it's unlocked a lot, but on the other hand, it hasn't overtaken everything. One of the things I often teach folks to do is we often start with a very simple model, then go to a more complex model. In the cases of areas like images and videos, the simple models just don't work that well compared to the more complex deep learning models.
Makes sense. So, as you've pointed out, we've seen some really amazing developments from this science, but certainly it's not a miracle cure, which kind of leads us into our primary discussion. A paper came out in Nature that caught your attention. For those who may not have read it, could you share a quick synopsis of what you read there?
This was a paper published in Nature, and it used deep learning to study aftershock patterns following large earthquakes. And so the idea here was we had different data about earthquakes, and we wanted to be able to classify and identify whether or not aftershocks are likely to happen.
So I don't have a sufficient background in that area to really kind of judge it from first principles. If someone said they were using deep learning to predict lottery numbers, I could discount it immediately. If they said they were using it to predict the stock market, I'm going to scratch my head for a while. What was your impression about the possibility of using deep learning to solve problems like this?
No, I was very excited when I read the paper of being able to take deep learning to be able to solve a very complex phenomena like earthquakes. But what happened is as soon as I started taking a look at kind of a careful look at the paper, I noticed that although they jumped straight to using a 6-layer deep learning neural network, they didn't include things that typically most data scientists include, such as a baseline model, that simple starting point, and how much better their model is than that simple starting point. And so that got me kind of scratching my head, wondering really how much value was the deep learning model adding in this case.
Gotcha. So that process you were describing of start with a simple model, it seems like they might have just skipped ahead in this paper. Is that one way to look at it?
Yeah, exactly. That's how I kind of read it when I didn't see any simple baselines for that.
One thing that doesn't always get asked about deep learning because it sort of purports to do feature engineering for you in a way, but machine learning, one of its the big challenges or big secrets to making it work, in my experience, has been very clever feature engineering. Did they do anything like that, or do you have a sense, even in general, of someone working on a simple model, what sorts of things might they want to know that would be helpful in predicting earthquakes?
So this is an area really where I was out of my domain. I'm not an earthquake researcher. So having that local knowledge, that subject matter expertise to be able to figure out what types of features to engineer, for example, to improve the performance of this, was something outside of my scope.
So I think I'm trying to think of comparable problems. I started thinking about the weather, and it's apples to oranges in a way. But if someone said they could predict the weather tomorrow, I would give them a lot of plausibility. If they said they could predict the weather on today's date 10 years from now, a much harder pill to swallow. Can we explore the gravity of the claims made in the paper? What exactly were they predicting?
The paper isn't just trying to predict the likelihood of an earthquake, which might see as something like a weather event, which might be very difficult to predict. But they were looking at aftershock patterns after a large earthquake. So this is a bit more of a tractable problem to be able to use a predictive model for.
I've seen a lot of projects which are sort of, they begin as copy and paste jobs, right? You take ResNet or some established deep learning architecture and you throw it at a problem and maybe evolve it. I'm not saying that's the right technique, but that's a technique I often see followed. Did this 6-layer model that they were using, did it follow any of those patterns that listeners might be familiar with?
So for someone inclined to use deep learning, that the approach that they used was not unexpected in terms of using tools like Keras to build a neural network, maybe repeatedly adding layers until they got a suitably high performance.
Gotcha. And what did they report then empirically in terms of the results they generated?
So there was a number of different results that they generated, but one of them was a metric for how accurate the model was with an AUC of about 0.85.
AUC is one of those numbers that I know its definition, but kind of like Pearson's R coefficient, I never know sort of what context to put that in. Could you, in layman's terms, say like the impressiveness of the model or something along those lines?
Well, I think the impressiveness always comes from when you have another benchmark to compare it. So here, the AUC of 0.85 was compared to kind of a naive benchmark of a very simple physical model approach. So not a machine learning model, but a physical model approach that had a benchmark of about 0.58 AUC. For those folks that are unfamiliar with AUC, the quick synopsis of it is AUC goes between zero point 0.5 for random to 1 for we've completely predicted every instance correctly. So that difference between 0.58 to 0.85 is a sizable jump in performance.
Yeah, absolutely. And in fact, one that we don't often see without incremental jumps, in my experience, if I think of things like ImageNet or whatnot. So when they were reporting all those details, you pointed out something that was especially interesting to me. How did the training and test sets turn out in terms of performance?
After I kind of read the paper, I started to dig into it a little bit because I wanted to see, could I, for example, improve upon the performance of the model? As I started digging into it, one of the things I noticed is that when I built the models, that the performance on my test set actually was much higher than the training set. And this is the train and test set that the authors had used. Now, for those folks who have done machine learning for a while, know that that performance, if it's much higher on your test set, data which your algorithm hasn't seen before is much better than what you've trained on. That's an issue. That's a kind of a yellow or red flag that there's something going on wrong with your model shouldn't be able to learn more than you've already taught it.
Although I have found that some deep learning practitioners have a bit of folk wisdom that, especially I see this in the image recognition community, that the network is sort of allowed or expected to overfit just a little bit in the sense that maybe, if you're doing some sort of face project with faces, it's actually going to overfit / memorize some of those faces while at the same time learning the, underlying manifold of features, if you will. So I don't know if you approve of that point of view, but do you find that that's common? And if so, would you give a certain amount of slack? Maybe not as much as the authors wanted to take, but how much slack do you think before we get the yellow flag?
Yeah, no, so that's a little bit of a different thing. Overfitting is when we learn and we memorize that training data, but then when we try the new data, it doesn't work as well. Here it was the opposite. When the model learned the training data, it actually did much better when we gave it new test data. The reason for this is what we call leakage, that there's been some information that has leaked between the training time over to the test time, and that's what's causing a much higher performance on the test set.
And are there any formal ways we can measure that leakage?
Typically, one of the techniques is we just look at that difference in performance. I mean, anytime your model does better on data it hasn't seen before compared to the data it has been is a red flag.
Thanks to this week's sponsor, the Flatiron School. Change careers with confidence by enrolling in the Flatiron School's Data Science Bootcamp. They have an in-person option in a number of cities, including the 4 most populated in the U.S. See if yours is on the list. And if not, look into their online option. Best of all, if you head over to flatironschool.com/dataskeptic, navigate down to where they lay out the curriculum. They have a really great user interface for browsing through all of their modules in this course. Let me highlight Module 6, Deep Learning and Natural Language Processing. They'll cover the statistical methods like n-grams, POS taggers, context-free grammars, regular expressions, and the neural network stuff like Word2Vec, CNNs, and more. But the Flatiron School isn't just that curriculum and that course and all the instruction that goes along with it, but there's a number of additional perks. I want to highlight one, their career services. The Flatiron School has a proven track record of student job placement. They have a dedicated career services team that works one-on-one with every student on a dedicated job search, which includes developing an employer pipeline, resume review, interview prep, and to help you tell your story to get the job you want. Check out their site to see a big splash of logos of all the places their students have wound up. If you're looking to switch careers, level up, or just learn, you owe it to yourself to see if the Flatiron School might be right for you. Head over to flatironschool.com/dataskeptic. Once more, flatironschool.com/dataskeptic.
Where do you think deep learning should fit in? Should practitioners need to get PhDs in machine learning before they apply it, or how can this be a useful tool for scientific inquiry?
That's a really good question. And it goes back to kind of data science as a profession. And one of the things that's changed is nowadays we have lots of people from a variety of different professions jumping in and starting to use the machine learning and data science tools. And one of the things we have to be mindful is that we need to ensure that everybody knows the fundamentals, that they understand issues like leakage, how we can use techniques, like in this case, group partitioning to prevent against that leakage. Because otherwise, issues and mistakes like this are going to continue to happen.
I'd love to unpack that technique which we haven't mentioned before, group partitioning. Could you share a definition and maybe some intuition as to why it's useful?
In this case, the data set consisted of about 130 different earthquakes. Some of those earthquakes actually happened right after each other, very near in the exact same location, maybe a day later. In other data sets, maybe you have customers where you have multiple rows for a customer. What we want to do with something, a technique like group partitioning, is make sure that that information for a particular earthquake or a particular customer, we don't split that between the training and the testing time. That information, when we're learning about an earthquake, we're not going to test on that exact same earthquake. That would cause that leakage issue. So group partitioning ensures that we put all the customers together in the same partition. Either we test on a particular customer or we train on them. And this is a technique called group partitioning that's widely used in machine learning to avoid these issues.
So in this case, it was sort of obvious to a machine learning practitioner, perhaps, that this is something you need to apply. But on the surface, it feels like an easy mistake to make. I know I'm worried about leakage, so I do a randomization of my training data, and then I do a test training set partitioning. It feels like I've done my job. It feels like you're following the procedures, and then you learn yet another rule. Is there a infinite series of rules here, or just, a finite number of techniques that need to be learned, and then you're all set?
So I don't think there's an infinite amount of rules to learn, but I do think there's some basic grounding and fundamentals, and especially when we talk about some of the nuances for when you set up that initial training data. Group partitioning is one. Another one that people will often use are things like date time partitioning, where for example, we train on earlier data, test on the most recent in order to prevent leakage over time. So I think there's only a handful of these issues that commonly happen that we need to be mindful and aware of when we're building those machine learning models.
So deep learning is absolutely here to stay. I don't know that it's going to change every single field and industry and all that, but it's certainly having a big impact. With that in mind, what should the machine learning community be doing to help, I don't know, either evangelize our techniques or do something to help people, outside of our community make fewer errors using our tools?
So I think there's a number of things we can do. I think first, as a community, we need to ensure that we set up some best practices, that we have guidelines for how we do this, and that we start to somewhat enforce them or talk about them, especially as new people just jump into the field, right? Read a couple blog posts and go build a model, that we make sure that they're following the best practices of the profession.
This paper in particular that we've been discussing got quite a huge response, at least on Reddit and I think on several other outlets. Why did this really go kind of viral?
I think this struck a couple of different nerves. So I think one is there's been a thread around reproducibility in academic literature for a while, where there's been concerns that people will put out papers and others go and try to reproduce them and they're not able to. And so this was a case where we went in and tried to reproduce it and found some issues with it, showing the value of that reproducibility. There's another piece of this as data science as a profession and how we're going to police these boundaries. As new people start to adopt and use these technologies, how are we going to ensure that they follow those communities' best practices? And then I think the last piece of it is the influence of professional institutions in publishing. One of the reasons this paper got so much attention was an author was from Harvard, another one was from Google, another one was from Nature magazine. And I think there's some feeling within, especially the Reddit community, academic community, that some of these are a bit more privileged, whether it's because they can essentially have these full-time researchers working, writing papers for places like NIPS that crowd out other researchers. So I had a number of other academics from kind of smaller institutions that were very happy that I pointed out the issues here.
One of the success stories of this whole discussion to me was that you had access to do that reproduction and that this is sort of a very healthy part of scientific process. Could you talk about where you started from, what you did in terms of reproducibility and what you found?
One of the great things about this paper was they made the data freely available, as well as the code that they used for building the models. So this allowed me to go in there, be able to look at the data, be able to look at the model, and go in and try to reproduce it for myself.
What does that entail? Obviously we'd mentioned it uses Keras. Did you have a big expense in standing up a cluster, or what were some of the nitty-gritty parts of this?
For this particular model, it used Keras, but it also used some files that were a little bit larger file sizes as well. So it was a little bit of work around that. But this model actually runs quite easily on a laptop computer. I was able to just do it on my good old MacBook. This is also where I've put notebooks available on the web where anybody can go in and essentially rerun this analysis, and it does not take very long.
Very neat. So I like that in that it's open access, open science. If I wanted to, I could go clone your repo and take a look at everything myself. What has been the feedback in that regard? Have you heard from the original authors or any other machine learning researchers on the topic?
I have not heard back from the original authors, but part of one of the reasons why I actually finally published the blog and published the notebooks to make it reproducible so anybody could run the models on the data themselves was I was contacted by some other researchers that actually come from the earthquake community. They're academics in the earthquake sciences, and they also had noticed some problems with the paper. And so at this point now, I'm collaborating with them on a larger article that will fit within that academic community discussing the issues here.
The other day I was thinking about what if I, for some strange reason, decided to make this line of inquiry my life's work. I wanted to get into the earthquake field. Obviously, I'd need to educate myself about plate tectonics and all that sort of stuff. And I would certainly want to bring machine learning to the table to help in this. But I'm also then wondering, well, where do I make an impact? For example, perhaps there's an effort where I should go out and blanket some area with more sophisticated sensors or, get into IoT stuff so I have better data. Or maybe I do need just a wider corpus and the existing techniques are good. There are these sort of hard multidisciplinary questions we have to answer. Do you have any thoughts on how a researcher, especially one who may not have a machine learning background, decides how to take their best step in the right direction?
Yeah, these machine learning tools are very powerful for researchers. And for researchers that are just dipping their toes into it, right? We all know that there's a wealth of information in online communities for people to skill up themselves. But I also think it makes sense, especially for those first few machine learning projects, that you work with somebody that has a bit more experience in it, that can kind of show you the ropes and make sure that the models that you build are actually capable.
Do you think that there's room to evolve the peer review process here? Should we have regular reviewers and then machine learning reviewers who check methodology or anything like that?
Oh, as someone who's been an academic, right, after every paper and kind of looking over the papers I still need to review, always want to find a way to improve the peer review process. And there's lots of ideas. It's not an easy thing to review. It kind of reminds me of, right, it's kind of the worst form of review except for all the others. I think, though, insisting on having the data available, having the source code available so others can reproduce it really helps lower the barrier to identify issues in papers down the road. Some of the other things we're seeing are movements towards having open reviews where anybody can comment on a paper. That opens it up as well in terms of peer review.
So earlier we'd been talking about, starting with a simple model and working your way up. I like that sort of iterative process. Do you have any, folk wisdom or best practices for how a person can execute on that for their particular needs?
I always encourage folks when they're building models to start with a very simple baseline. Could be a logistic regression for a problem like this. It could be maybe a random forest. But having those simple baselines that are easily understandable are often a good stepping stone before jumping into building that deep learning network.
Yeah, and along the way, there seems to be sort of a trade-off between interpretability and hopefully accuracy, because why would you reduce interpretability if you weren't getting more accuracy? Do you have any thoughts or words of wisdom on how someone navigates that trade-off?
I have a lot of thoughts on this, and actually I'll be speaking at the Open Data Science Conference on interpretability. But generally speaking, there is a bit of a trade-off between interpretability and accuracy. If we want to get that last little bit of improvement, often what we're going to have to do is have models that are a little bit more flexible, that are a little bit more nuanced, that get a feel of the data a little bit better than our engineered features are able to. And so in this case, and often in these cases, we're going to trade off a bit of interpretability for accuracy. But I will point out that we have a number of useful tools out there that can really help us explain any model and really add a lot of transparency to them. So even neural networks, even deep learning networks, we can apply tools to better understand what's going on inside them.
Well, where can people follow you online?
I'm on Twitter, RajCS4. I think that's all I really got.